we are awfully out of our time, so I take a liberty to compress this panel discussion. Certainly we have at the same time to enlarge the finish of this panel discussion by 5 minutes. And now to start our work, I have a pleasure to invite the panelists, the participants of our discussions. And I would like to invite Alice Valkamova to take the place. Please take your places here. Then it's my pleasure to invite Laszlo Yankovsky. Okay, you can do that. And sit down, please. Sit down. He wants to be over there. Okay. Now, also, I invite you, Professor German, to take his place. And then Jan Kaspar also is participant of this discussion. The same has to be done for Johan Blow. And finally, Antonio Sidotti, I hope he's here. Also take your place. I have to have only okay. So I didn't forget. You are here because I counted for 6 people. You are here. Okay. Now we have questions. We have questions we have to try to discuss because we have not much time. Certainly, the questions are so large and so general that it takes maybe a whole conference to discuss all of them in full totality. But nonetheless, I will try to start our discussion, and I would like to invite Professor German to start discussion. The first question concerns the problem of principle which underlie the diffractive studies. And try to limit with 3 minutes in order to give to others.
I have prepared a brief.
No, it's not. What I would like to raise, and we want the panel, is that the panel discussion is not the second talk.
It's completely different problem. It has nothing to do with my talk.
Yes, but we will not talk. That's what
okay,
I would like to raise. If you can do that in words.
Okay. But people would understand. What I would like to say that the picture which I described implies somehow that there is very important problem which is not solved yet in diffraction scattering, that is how protons are compiled with partons, and what are the coherent states of partons and what are incoherent states of partons inside the protons.
So you rush directly to the first.
Yeah.
Okay.
Yeah, that's my question.
Can I conclude that you have no answer to the first question? And you prefer something more concrete?
Which you want me to speak about all 5 problems?
Okay, yes, we started from the first one, and you prefer to start from the first one.
I prefer to start because for me it's
Go ahead.
It looks as more important and unsolved problem yet, that we don't understand coherent and incoherent states of partons inside of protons, and how they, I can refer maybe to recent work by Martin and Riskin, which tried to answer to this question, saying that there are coherent states and incoherent states of partons plus a photon inside of the proton. Inside of the proton. And so this is in theoretical language. It's described in such a way that proton as a whole emits the photon gamma, which was coherently inside of the wave function of the proton. But also there is incoherent stage, where that proton is described as three patterns, and one of the patterns emits photon. These are different graphs, and they can be taken into account and can be applied to hair data.
What's your answer to this question?
My answer to this question
Yeah.
is I would like, not answer, but I would like to put a question to those who deal with pomerons.
Okay.
How to include coherent pomeron and incoherent
Thank you very much.
pomeron.
Thank you, sir. But if
That's all.
a theoretician who actually initiated this question has no an answer, so it rests to me just to ask other people, and maybe Alisa, what can you say about this?
No, I'm an experimentator, so I'm experimentalist, so I don't know if I'm the good person to speak about it. Maybe I have some.
So, just to finish with that, in your case, you hesitate to answer this question, and so you can choose the question you like and to continue.
Okay, so as an experimentalist, I have some doubts. There is I have no doubts, but in theoretical models, they can be pomeron or they can be not. Yes, of course. Yes. Because in principle, I just shown this analysis of those which gives some preference to some two model or something like this. So in this case, it is not evident we need this DPS and other stuff. So I of course think that for such conclusions we need much more study than just a for distribution. Yes, but in principle, I don't know.
Okay. No, you have replied already. Thank you very much. Because the second question you have chosen, you gave a definite answer that the pomeron is two gluons. Okay, that's very good. And I want to ask other participants. For example, you do you agree that the pomeron is two gluons?
Well, I mean, I always find it a bit difficult to answer these kind of questions because I'm an experimentalist.
You investigated. How?
I mean, the thing is that you rely on, so if you think of this exclusive Chi-C production, which is only possible with the exchange of two gluons because of angular momentum and spin conservation. So they could seem to point to this effect. However, from the data, it's not so easy to disentangel because of the fact that we do not have 4-pi coverage of the interaction region. So we cannot really claim that the two protons do not dissociate. So,
What?
okay, so the problem with LHD is that you do not have 4-pi coverage of the interaction region. So you cannot say with 100% certainty that the two protons did not dissociate.
That's your answer to the question, what is a pomeron or what?
No, it's the answer to interpreting the experimental data. So the experimental data seems to point there being
okay.
a pomeron. But,
So they do not dissociate. Oh, you think so?
For this you need a theoretical input in order to interpret your data. So it's a little bit like the snake biting its own tail, yes?
Thank you very much, but we have just begin to mix questions. I don't think it's bad. So maybe Jan can find out something which he would like to clarify. I can, if you have not in front of you.
I don't know whether I can clarify definitely for the second question. My answer would be a little bit provocative. So when you say the pomeron, my question would be which pomeron do you think? Because
this is a part of this question.
Yeah, I mean, different groups of people arrive with this concept of Pomeroy from different aspects. So we know there is something like soft Pomeroy as
For example,
a
soft
super critical trajectory. The people from BFKL arrive at different Pomeroy. So I don't really know what Pomeroy is, but definitely most likely there are different Pomeroys of different ages, describing probably different kinematic regions.
So you say that the Pomeroy is,
not
by no
Pomeroy.
means is unique.
Yes.
So we have many options for the Pomeroy, so it's impossible to answer this question.
I wouldn't say it's impossible, actually say I don't know the answer.
Okay, very good. So let's proceed further. You have to add something.
Could we
You're
go
welcome.
to question 1, maybe?
Yeah.
From the theoretical point, I don't have anything to say about this, but I do have a question to the theorists in the room. And so it seems that in order to learn something definitive about diffractive studies, analysis, you need to mean your data or to show your data as a function of impact parameter B. And but however, it's very difficult to measure B experimentally or to determine B experimentally. And so my question to the theorists would be, how can we determine the impact parameter of a collision?
Oh, you think that this is a question of principle?
Yes, because if you do not know what B is, then there is nothing you can say about this diffractive study.
Yeah, that's. I would say that this is very important question about that. Maybe you will clarify.
I can answer this. Surely nobody can measure P directly, but that was what I spoke about inelastic processes. In CMS, we studied the two jet events and underlying events at high multiplices, at very high multiplices. And in the region of from 100 charged particles to 140 charged particles, we found the strong decline from all Monte Carlos. And then we started to analyze many characteristics. I showed only one of them, which is most impressive, that at high PT jets, they develop also plateau, which is related to this plateau in B. And then at low PT, they start decrease, because high PT corresponds to small b, and low PT corresponds to large b.
So I have to interrupt you, because it seems to me that you begin to describe complex things. We deviate from the very question, because the very question is formulated clearly as the problem of principle. When I say problem of principle, what I mean, maybe I have to explain. When we say what is a problem of principle, for example, was recently for the standard model, maybe still is does Higgs exist or not? It was really a problem of question of principle for the standard model, for the electrolytic sector. If we have such kind of questions in the diffractive sector, that's really the meaning of this question.
Maybe I will try. It seems me that the important question is this question of factorization breaking in diffraction, because it is a problem which arose many years ago, because when Hera measured these structure functions in PDF, yes, and then it was applied for Tevatron, and there was this observed this factorization rate. And this is still, I think, not fully explained, yes, what happened, yes. For there are several models, but they are not so well maybe supported by the data, yes. So we observe it, yes, in food production, but it is not, it is in there were some attempts to explain it in a leading order QCD, but the question is how it will look in next to leading order. It is also observed in LHC, yes, in proton collisions, but the question is if quantitatively, it probably depends also on some kinematics, yes, and, but there is no prediction.
Thank you, thank you. At least this is clear.
That is why I mentioned this paper of Martin and Rizke. They explained just this for Hera.
We have to finish with this question, but what is our problem? Maybe I will describe it when we finish. I will summarize the discussion after that concerning the first question. So let's come to the third question maybe. What is the true asymptotic regime, asymptopia, if any? Because what I mean, so very often we can meet the opinion that there is some region of energy starting from which some stable regime onsets and cross-sections they begin to behave in predictable, stable way, and so on and so on. And this is a question: if such a region exists at all, if we are close to it, if yes, if we are close or far from it. Who will start? Maybe you. Because you don't work. Yeah.
No, I don't work, but this is the worst question.
Yeah, it's really, yeah. In my notes, I put the question number 3 is the one empty, as you can see. So I was very lucky to have this question. So yeah, difficult to say, and also difficult to prove, because we know that right now and next year we are going to 13 TeV at LHC, so we are going to have an increase in the center of mass energy, but it's from 13 to 2 TeV. There is no plan to go up. So it's difficult to me we can probably say anything experimentally, but it cannot be proved. I mean, so maybe I have a comment not on principle, which is question number 1, but from an experimental point of view, all this kind of physics, diffractive physics, can be done at LHC with in special conditions. So we are the only one that like a small number of pileup and a high beta star and things like that. I think that there should be, it's not still clear to me, and this is also a question to the other panelists, if we are statistically limited, if we need more data in this special condition that all 95% of all other analyses don't like because they want to be innovative. But still, I think that our kind of physics measurement are useful also for input for all the other analyses. For example, like mentioned, understanding the underlying event and things like that. So the question also to you and to us essentially is: are we statistically limited? Do we need to ask for other special runs to LHC? Our question to the machine? Could they be better motivated and things like that? So.
Okay. Coming back again to the third question, I would like to ask again Igor, because he remembers old times when 4GeV we were considered as a asymptotic region already, but now times changed very much.
Yeah.
But are we still there, or we close to something or not?
Yeah, I would say that true asymptotics is very hard to reach, and it's especially hard to get knowledge of it from inelastic collisions. In my opinion, it's a very difficult problem. But in elastic collisions, just there is a way in which I see how, in particular, how this parameter Z changes. Because everybody said that in the limit we come to the black disk limit. No black disk limit exists. It's a completely wrong assumption that in asymptotics we come to the black disk. If you look only at the unitarity condition, you predict that it is a tube inside of which protons fly freely and interact at the periphery. So it comes more or less to one pion exchange model, even which I proposed in 58.
So the atmosphere gets more and more rarefied again.
Yeah, Again,
Okay.
very
That's your point.
strange atmosphere.
That's your point. Thank you very much. Well, so if maybe prior to come to the last question, I would like to ask people from the audience, maybe they will add something in the form of questions or comments or something like that. For any of 4 questions which are already discussed here. So no opinion about that. Okay, but maybe there is a reason for that. I will try to explain it why. So let's come to the final question. I will. Yes. Yes.
May I say something to question number 1?
Yeah. Very good.
What I found, at least in the soft sector, there is a gap, and it's not a repetitive gap between, let's say, the theorist and an experimentalist. So you know there is a number, 10, 15 models, using really large number of different mechanisms to describe the data, and then we come with a measurement and everything which counts that the people refit data, and there is no single mechanism which is excluded. So I think we are kind of failing to use the theory measurements to exclude possible mechanism or not. So I definitely would think it would be better if there is more interaction between theory and experimentalists. If they were supposed to could tell us, try and measure this, and then we know whether we should go left or right. But I don't see this happening.
Okay, thank you. That's very valuable comment. And maybe somebody wants to add to the first 4 questions prior to come to the last one. Or you have said already what you had to say. Okay. Now the last question surely sounds not very maybe clear. If QCD has anything concrete to say about diffractive scattering, because first of all this concerns people who are involved into QCD studies of diffractive scattering, and I don't think that our friend experimentalists are very deeply involved into this business, but nonetheless as users in some sense. So because they, time after time, they made some kind of references and so on, and we have seen some opinion about that.
Tell me your opinion.
After that, according to your opinion, let's just start from you and then go by turn. What's your opinion about QCD? Because QCD is an official theory of strong interactions. It was announced many years ago in '73 as a theory of strong interaction. That was said, and in many conferences you have said that QCD is in excellent form as a strong theory, strong interaction theory. So, what's your opinion? Is it so? And the QCD can give you some insight or something like that.
I certainly would not want to say that QCD is useless or not. I mean, it's difficult to apply it. Yes, I mean, if you try to calculate something that non-perturbably, then the calculation still isn't finished.
No.
So, I mean, from the experimental point of view, we take data and we try to use the data to prove or disprove models. A model, of course, involves assumptions and not necessarily QCD. And if I think of my own talk and talk with other people, then what we use a lot are phenomenological approaches where we fit data using power laws or other models, assumptions. And now the question is, can this not be predicted by QCD? Is I think a question that we should ask our theoretical colleagues more than our experimentalists.
Thank you. Yeah.
Yeah, well, this is the same. I don't have really an answer to this. I can also state that I hope it has something to say. And it's not to me a question of QCD, but the way how we can handle trick QCD. Yesterday there was someone speaking about supersymmetry and said that actually it changed the way how we see the cage theories. And actually now there are ways how this can be handled non-perturbatively. There are solutions. So when I heard this, I said, okay, maybe at some point, one day, someone can take the QCD and actually make a solution which can be applied to the kinematics of different scattering. I hope.
So theorists are not hopeless. Thank you.
We are not hopeless. We don't know the theory.
Okay, I think that QCD has a very restricted area of application, maybe at very high transferred momenta, and it's not even for sure. But what concerns lower transferred momenta and low PT, my answer is no until we solve the fourth problem.
Okay, thank you. Alice?
I would support this. We are using QCD always when there is a hard scale. Yes? So it should be or Q square or PT square or something like a square of the mass of vector mesons and so on. Yes, but we need also this soft physics. We need the Regge phenomenology. Without it, we will not do many things. For example, this is the PDFs. Yes, so we have some peaceful cooperation of these two methods. Yes, of these two methods, and we are using or one or second one, but as Igor Mikhailovich said, so it's not solved. Yes, so the major part of diffraction, I think we don't understand at all. Yes.
Thank you. Antonio?
Yeah, I can only agree with all of you. So, QCD as a field theory finds little application in small, in soft, let us say, QCD. We have, what we have tested so far are phenomenological models. Yeah, the important thing is that these models should be predictive. Otherwise, if each time we change, we go up in energy or we change process, whatever, we need to retune or refit things. Well, okay, it's good, but it's not predictive. It's like Ptolemaios cycles, you remember. So.
Thank you. So now we have almost have no time, just several minutes, a few minutes actually, to summarize this quite compressed discussion. What I have to say about all that. First of all, what concerns the very subject, I mean, diffractive studies, or soft physics, or forward physics, there are several names for this field. This is very often considered by not only by ordinary people, but even inside the community, for example, as a kind of not very important, sometimes even some kind of obsolete physics, which was formulated many, many years ago, and this is something of the second hand. And that's not true absolutely. This is due to maybe it's we have to blame theoretical people who could not explain properly to others. And the actual, what is the diffractive studies, for example, at the level of LHC? If you take diffractive experiments at LHC, this is absolutely peculiar experiments, it's a peculiar program of investigations, absolutely different from the rest of experiments at the LHC, because of the rest of experiments at the LHC deals mostly with short distances. They use huge energy to penetrate to shorter and shorter distances. While in this field, I mean diffractive scattering, we do quite the opposite. We use higher energies to penetrate to larger distances, both in transverse direction, because you know that the slow grows and the interaction region grows, but very slowly, and also longitudinal directions also slows with energy. Now you can say that we have already had large distances when investigating lower energy physics. And in this case, we can ask ourselves, is one Fermi at 100 MeV is the same one Fermi at 7 TeV, for example? I think that the answer is a negative, and we explore not the same, which already passed. We explore just new territory, which is absolutely unknown. This is terra incognita. And that's why I think the diffractive studies in no way can be considered as something second-hand or obsolete or marginal. It is very important direction of investigation from many points of view and from the point of view of principle. Now, where we are now. First of all, the state of affair is such that we have to say many thanks to our experimental colleagues, because they do everything during many, many years to supply us with data. And this data certainly not always are of the best quality, but from the recent measurement at the LHC, I think we can be satisfied. Maybe they will be improved. But what concerns theoretical part of this field, unfortunately, it is related, surely, with QCD, with models, with what concerns models. First of all, a few words about that. The models which are formulated and with which the data is very often compared, it's very difficult to interpret, both in the case of confirmation or if some model just fails. Because if it fails, it's nothing special for people, just maybe personal tragedy for authors. If it will describe some part of data, again, it will be very difficult to disentangle what from the results go in this model, because the model is not QCD pure. It is supplied with many, many extra assumptions, which is very difficult to understand what is it. And so it's absolutely impossible to make, if the model is successful. And after that, authors very often, they cannot even say what does it mean physically, to explain to any people in the street, for example. We can explain to people in the street that if you have discovered the Higgs boson, this is something which gives us mass and so on. It's absolutely clear. Taxpayers will be content with it, that they pay money for something. But if you approach them and say that you have measured total cross-section, it is 100 millibarns instead of 120, I don't think you will be very much inspired about it. So there is a need in a very serious work from the theoretical part of community, namely in QCD, because what we have done during last 40 years, pretending to be working in QCD, may be summarized by one unpleasant word: nothing. And let me illustrate this situation with a picture. "40 years ago, first investigations of diffractive scattering, I mean, first of all, the regular trajectories, and not even trajectory, but the intercept. This is one single number. The people calculated this one single number due to 40 years. Finally, they came to this answer, which is absolutely cannot be considered as good or something like that. Why? It's clear from the, what is written here. It depends on absolutely arbitrary mass scale, for example. It can be done, it can be given to it any value, so no value at all. First of all, also I would like to notice that actually in the framework of QCD, the only result we can obtain now, that in the framework of the QCD, this number, the intercept of the regular trajectory, does not on the calculate constant at all. So it's impossible to calculate it in the framework of perturbation theory. So after 40 years of walking around this desert in the search for one single number, the intercept, we are still in very bad position, but this is our fault in front of our experimental colleagues. We are dragging far behind them, excuse us, and we promise maybe in several years to make some efforts to correct such a sad situation. This is my conclusion. Thank you very much.
What they should tell to people on the street when they ask what they are doing. So
Yeah.
you can tell, okay, so there are Higgs and these other QC processes, so these are maybe 1 per mil of, we understand maybe 1 per mil of, or even less, much less, of the interactions which are happening, yes, which are interactions of the interaction and so on. this 99.99999, this is what we are doing and what we are trying to understand. Nobody knows.
In terms of cross sections, yes, yes. We make cross sections which are very big. Yeah, thank you very much. It's a good argument.
So majority of the
Something big always works.
Yes.
Okay, thank you. Okay, if no more questions, comments, and so on, so we'll finish and we'll meet each other after the lunch.